Greetings and welcome, friends. Mr. Waddy here. What a great day to be learning the maths. So good. So this is section 3.4. We're talking about graphing linear equations in what's referred to as standard form. Ready? Do I have a sneeze? There it is. Woo! That was Man, that was like suspenseful. You thought it wasn't going to happen for a minute? Wow. Man, this is my favorite intro yet. So let's see. Let's talk about standard form of a linear equation. This is a different way that I can write an equation. Let's see. Looks like I've got an invisible table here. That's weird. I'll try to ignore that. It says the standard form of a linear equation is ax plus by equals c, where a, b, and c are real numbers, and a and b are not both 0. Okay, so it's possible if a is 0, then 0 times x is 0. If b is 0, then 0 times y is 0. But I do not want an equation where both of those things get zeroed out. So, actually, they just did that. Consider what happens when a equals 0 or when b equals 0. That's what we just talked about. When a equals 0, the equation becomes by equals c, or y equals c over b if I divide both sides by b there, right? Divide both sides by b, that's what you'd end up getting. So y equals a number is what I would get. And because c over b is a constant, you can just write this as y equals some number. When b is equal to 0, the capital B, the 0 times y would have been 0, and I would have had a times x equals c, and I could have divided both sides by a, and I'll get x equals c over a. You can write x equals a as that constant, as kind of like a simplified situation. So these two things we're going to be particularly interested in regarding this up-and-coming core concept. It turns out that it is possible to graph horizontal and vertical lines, and you can usually detect what they look like instantly based on their equation, at least if it's written in standard form. So horizontal lines, horizontal, think horizon, okay, horizon. So like if you saw the sun setting on the horizon, right, a horizontal line is like that. And a horizontal line will be of the form y equals b. Y equals b. And I think that this is super opposite of what I would have expected, because my x-axis is horizontal, and that's got an x. And now we have a horizontal line, and it's y equals some number. All right, so that's kind of the opposite of what I would have thought. All right, I don't know if you guys think like that. And so to be honest, one of the ways I remember this is I actually remember, if it's a horizontal line, it's y equals, not x equals. It's the opposite of what I would have thought. And I use the kind of potential error to become a means for me to remember. Now, the reason that y equals a number is a horizontal line is think about all of these points on this line. So if y equals b, all right, think about what happens. If I said x equals 0, what is y equal to? Y is equal to b. If x is equal to 1, what is y equal to? Y is equal to b. When x is equal to 10, what is y equal to? Y is equal to b. Y is equal to b all the time. When x is equal to pi, 3.14159, infinite, non-repeating, y is equal to b. And if I collected, when x is negative 2, y is equal to b. And if I collect all of those values, what I'm left with is a horizontal solution set. Also notice that it happens to pass through the y-axis, where? At the height of b. So if this was y equals 7, it would have been a horizontal line passing through 7 on the y-axis. Okay? Similarly over here, for a vertical line, which I know is not a function because it doesn't pass the vertical line test, and in fact, it Could I say it fails the vertical line test with flying colors? Is it possible? If you can pass with flying colors, can you also fail with flying colors? Maybe it fails with or it crashes with hues of grayscale and lack of color is how much this one fails the vertical line test. I don't know. I'm trying to think of an analogy here. But nonetheless, here we go. Notice that a vertical line will be of the form x equals some number. And once again, that's the opposite, because here, hey, the y-axis is the vertical line. And this x equals a number is a vertical line. So once again, kind of the opposite of what I would have expected. So try to make note of that, like memorize that idea. And so notice this makes sense, because if x equals a number, what do I get when x equals 0? Well, nothing. There is no point when x equals 0. What do I get when x equals 1? Well, nothing. There's no output when x equals 1. What do I get when x equals 2? Nothing. What happens when x equals a, or 3, I'm pretending in this hypothetical situation? If I plug in 3, I get all possible outputs, everything. Everyone's like crowded, like, I want to be here. I want to be the one in this spot. And they're all crowding into that space. So that's what I end up having, is all of these points. I'm plotting all of the points whose x coordinates occur at A for any given y coordinate, okay? And so that ends up being a vertical line. So to graph these, it's actually not too difficult, I don't think, as long as you kind of remember these little facts. So let's do this, this first little example here. And I think I'm going to actually graph these both on the same coordinate plane. There we go. Here we go. I've got my coordinate plane. So let's see. For graphing y equals 4. Now let me ask you, y equals 4. Do you think that's horizontal or vertical? Oh, so tricky. So tricky. Y equals 4. The y-axis is vertical, but y equals a number will be horizontal. So this is going to be perpendicular to the y-axis. Or it's plotting all of the points whose y-coordinates are 4. So that would be like 1, 2, 3, 4. So that'd be like this point, and this point, and this point, and this point, and this point. All of the points whose y-coordinates are 4. All right, so let's actually, we'll tell you what, we'll oh dear, man, my invisible, oh dear, guys, what happened? Why are my tools showing up invisible, friends? Come on, what's going on? That's a weird glitch. I think you guys agree. Have you ever had problems with invisible tools? You just can never find them when you need to. And then now I accidentally was stumbling across them when I didn't want them. Classic. Let's see. There we go. All right. Aha. All right. So I would draw the horizontal line like so. Notice it's y-intercept. The point where it crosses the y-axis is at 4, or it's at the point 0, 4. All right. So something like that would be that equation. All right. If I have x equals a number, I'm thinking of all points whose x coordinates are -2. So that would be like -2, 0. That would be like -2, 3. That'd be like -2, 10. That'd be like -2, 5 if I landed on that right. And so that's going to be a vertical line. And let's line this up something like. And so that's a vertical line. And what is its x-intercept? What do you think I mean by x-intercept? The point where it crosses the x-axis happens to be at -2, 0. All right, so x-intercept is the location where a graph crosses the x-axis. The y-intercept is where the graph crosses the x-axis. And actually, that's going to be this next core concept. Which question for the yellow line, where is its x-intercept? Where's the yellow line cross the x-axis? That it crosses the y-axis here, but where does it cross the x-axis?
Oh.
It never does, right? It's parallel to the x-axis, so it's never going to touch it. It's staying the same distance away from it forever. Well, this is the y-axis, and the yellow line crosses the y-axis, but it's not crossing the x-axis. Where do you see? Here, stand up and point at it. I just want to make sure I understand what you mean. All right, so the yellow line, well, that's where it's crossing this other equation, but the x-axis is the, right, here's the x-axis is this white line, and here's the y-axis is the white line. Yeah, so yeah, it does cross the vertical line, which actually, I think chapter 5 is when we'll talk about, maybe it's 6, is when we'll talk about intersections of lines, and that will be something that we're interested in. But notice this yellow line is parallel to the white x-axis. It never touches it. And the same thing for this blue line. It has no y-intercept. It never crosses the y-axis. So I just use the words, right, x-intercept and y-intercept. And these are going to be the means by which we are graphing today. This is kind of a nice little efficient means of graphing. So check this out. Let's see, the x-intercept of a graph is the x-coordinate, all right, of a point where the graph crosses the x-axis. So here is this orange line. It hits the x-axis here. If I'm talking about the x-intercept, I'm just talking about the x-coordinate. So it's equal to the number a, all right? It's not equal to the ordered pair. Although the ordered pair, I think you could argue, describes the location of that intersection. But that is the x-intercept. The y-intercept is similar, is where a graph crosses the y-axis. So notice, oh, I thought I chose red. No, I didn't. So here is that point. The y-coordinate is b there, and so the y-intercept is that value b. Now, I want to point out that notice an x-intercept will always occur when the y-coordinate is 0. Think about all of the points on the x-axis. Every point on the x-axis has a y-coordinate of 0, right? Here's 0, 0. Here, I'll just pick my color back here. So here's 0, 0. Here's 1, 0. Here's 2, 0. Here's negative 3, 0. All of those have 0 as their y-coordinate. And that's what this little fact is saying right here. And that fact is going to help us find x-intercepts. X-intercepts occur when y equals 0. And similarly, y-intercepts occur when x equals 0. So here's 0, 0, here's 0, 1, here's 0, 2, here's 0, 3, here's 0b, here's 0, negative 2. All of those have 0 as their x-coordinate. And so y-intercepts can only occur when x equals 0. And that's where these concepts come from. To graph an equation in standard form that isn't just horizontal or vertical, we can find the intercepts. Okay, I could find these two x and y intercepts and draw the line that passes through them. And to find the x-intercept, I let y equal 0. And to find the y-intercept, I let x equal 0. So x equals 0 for the y-intercept, and y equals 0 for the x-intercept. So let's do a couple. We're going to do as many examples as I can of this, because this is going to be helpful. Helpful. Help me. All right, so example 2, we're going to graph a diagonal line using what's called the intercepts method of graphing. So this line is in standard form. If I wanted to think about the standard form, I could have thought that a equals 3, the b equals 4, and the c equals 12. But I don't actually need to know those things right now. I just figured I'd point that out to you for the standard form. And if I want to find the intercepts, to find the x-intercept, I'm going to, for my x-intercept, So my x int, I'm going to set y equal to 0. Okay? So let's set y equal to 0. So this would be 3 times x. Oh, wrong color. Wrong color. Here we go. So 3 times x plus 4 times 0 equals 12. And I'm now going to solve for x. Notice, what is 4 times 0? 0. Awesome. And 3x plus 0 is going to equal 3x. So one of the nice things about intercepts method is it just kind of makes these super simple. El más rápido del mundo. Oh, it's the best. I love it. So to plot the x... Yeah. Agreed. So you are thinking like a mathematician as far as what's an efficient way to do these things. So let's see. Let's plot the x-intercept. If x equals 4, I'm going to go 1, 2, 3, 4. Right there is the x-intercept. Let's see. Did you already find the y-intercept? Is that what you were saying? Oh, no. I thought you were predicting what the y-intercept was going to be. To find the y-intercept, that happens when x equals 0. So I'm going to solve the same equation, but plug in 0 for the x. So 3 times 0 plus 4y equals 12. 3 times 0 is 0, as we were saying. So that's just the same as 4y equals 12. How do I solve for y? Don't pack up yet. You can stretch, though. You can stretch. Divide by 4, and I'll get y equals what? 12 divided by 4 is 3. So my y-intercept occurs at, in this case, positive 3. 1, 2, 3. And so if I want to draw this line, I now have the task of just connecting the dots. And so notice, like, these were the easiest points possible to find. Well, to get the x-intercept, you plug in 0 for y. To find the y-intercept, you plug in 0 for x. Once again, notice how opposite that is. Right? Super opposite of what I would have expected. But that's okay. Right? That's perfectly fine. All right. Oh, I've got all sorts of things blipping at me here. All right, reminders. Okay, so let us, I think, can I get example 3 done? Ooh, man, this is tough. This is tough. All right. I've got 1:45. I'm going to do more examples than I have time for and post it on the video. So you guys just keep following along. And we're going to do plenty of examples of this. You can watch the video tonight if you want, or during ACE block this afternoon. But I will end up getting to example 3. Here, try not to make too much noise with the chairs if you could when the bell rings. So let's see. Graph using the intercepts method. So here we go. If I want to find the x-intercept, what do? I plug in 0 for y. So x int 0 for y. Let me get some space here. So x intercept y equals 0. X intercept y equals 0. And for the y intercept, I plug in 0 for x. Right? Here, I can't see, my friend. So for the y-intercept, plug in 0 for x. So let's do these in both of these cases real quick. So plug in 0 for y, I'll get 2x equals 4. Plug in 0 for x, I'll end up with the opposite of y equals 4. That's an interesting problem right there. Plug in 0 for y here, I'd get x equals -9. Plug in 0 for x over here, I'd get 3y equals -9. So notice how quick I can do that, and now I just solve, divide by 2, divide by 2. Maybe I'll view this as multiplying by -1, just to opposite it. This one's already solved, divide by 3, divide by 3. And I get the following. So here the x-intercept is 2. The y-intercept is -4. See you guys later today. Here the x-intercept is -9, and the y-intercept is -3. So let's plot these points. X-intercept at 2 is right here. This one's x-intercept was -9. right there, just saving some color time swapping. Here the y-intercept is -4, so 1, 2, 3, 4. And here the y-intercept is -3, 1, 2, 3. Like so. And now that I have these intercepts, I can actually graph all solutions of this equation, the infinitely many of them, by just connecting these dots, drawing the line that has those given intercepts. Let's see if I can do that here. Something like this. All right, so there's one line, and over here, and over here, like this. All right, so those are the graphs of those equations, and I think this was way easier than making a table of values where it's possible you could have a whole bunch of weird fractions and things. Yeah, if you don't mind, just close the door when you head out. And I'm going to do this one last example for our internet friends and my future students here. Okay, example 3 from your book. And now Mr. Waddy is all alone. Don't worry, internet friends, I know you're still here. You're still listening. You're still watching this video. It says, okay, so here we've got a word problem. Step 1, it's asking me to graph the equation using the intercepts method. I'm going to set myself up with a grid here, like so. Probably have way more points than I need, but that's fine. So let's read this problem together. You are planning an awards banquet for your school. You need to rent tables to seat 180 people. Tables come in 2 sizes. Okay, here we go. Here we go. Small tables seat 6 people, and large tables seat 10 people. So the equation 6x plus 10y equals 180 models this situation. Now in the future, you'll have to write that equation yourself. Here they were super generous, they gave it to you. But I want to point out, x is the number of small tables, so 6 times x is the number of people that can be seated using those small tables. Y is the number of large tables, so therefore the 10 multiplied by that y, 10 times y, is the number of people that can be seated using those large tables. And I know that adding those 2 things together will end up equaling the total number of people that I need to seat. So let's see. So let's find our x-intercept for part A. Here I do that by setting y equal to 0. And so we're going to end up getting the following. So if y equals 0, I'm left with the equation 6x equals 180. Divide both sides by 6. And I get x equals, looks like 30 is the value for x. That's going to be my x-intercept. For the y-intercept, all right, y-intercept, that's when x is equal to 0. And so I plug it into the equation. So that's going to be, let's see. Wait a minute. Did I do this wrong? Did I plug? All right. Okay. No, we're good. We're good. So I got, yeah, x equals 30. And let's see. So I'm plugging in 0 for x. So yeah, so here we go. So I'll have 6 times 0 is 0. So this equation will be 10y equals 180. So in order to solve that, divide both sides by 10. And in this case, I get y equals 18. All right, so we've got to now figure out our axes for this problem. Now, I think I gave, let's see, 2, 4, 6, 8, 10, 12. Yeah, I think that I'll be able to fit the 18 for the y-axis, just counting regular boxes. But 30, I probably won't be able to fit. For the x-axis, I'll probably have to count by 2. So I'll have 2, 4, 6, 8, 10, and then I'll just count, label every other from here. So this would be 14, this would be 18, this would be 22, this would be 26, this would be 30. And that should be far enough for me. So let's plot our points. So our x-intercept is at 30, like so. Our y-intercept is at 18. I guess I should have labeled these two. I'm going to label every other, but these boxes count as one. So let's see, 2, 4, 6, 8, 10, 12, 14, 16, and 18. Thing of beauty, thing of beauty. And so I'll plot my y-intercept. And now the solutions are going to be all of the points that are on the line that connect those dots, and every point is a possible solution that makes the equation true. Now in this case, my solutions would technically not be the continuous set of points between these. Technically, they would be only the ones that land on a lattice point, which actually I don't have a great example of because my grid doesn't hit all of those things. But this is the idea, okay? This is the idea. And so any point that is a whole number on this line, whole number for both x and y, would represent a possible solution for this, right? Because x represents the number of small tables, and y is the number of large tables. Okay, so that's what those represent. So let's think of what some possible solutions of this might be and interpret what those mean. That's what it says. Find 4 possible solutions in the context of the problem. Well, it looks like one of those solutions would be 9, looks like 13. So that would be get 9 small tables and 13 large tables. Another solution looks like 18 and 7, right? So 18 small tables and 7 large tables looks like a solution. It's difficult to tell exactly where these landed, but essentially any point, like this one might be one right there, looks like 3 is the halfway point. So 3 small tables and 16 large tables might work. And I could check these points by plugging them back into the original equation and just verify that that adds up to 180. So for instance, 3 times 6 would have been 18 plus 16 times 10, that's 160. So that, that actually only adds up to 178. So that didn't work out perfectly there. Which is one of the limitations of graphs, but it at least gives us a ballpark idea of where we can land because graphs aren't perfectly accurate. But that's the idea, is that I can kind of pick some points on this, and that's what they would represent in terms of the real world problem. All right, so obviously I could just buy all small tables, 30 and 0 large tables, or I could buy all large tables. So 0 small tables, 18 large would be a solution. And so so that's what those solutions represent, and that's how we would end up having these work out. All right, so thanks for watching, friends. Have a good day.